The world we live in now is filled with data. Yet, for most of us, we spend a great deal of our time looking at data without knowing what it really means. There's actually a lot that goes on behind the scenes for the interpretation of data in order to translate it into something we can understand and appreciate. Data can be harnessed to do many amazing things. The value of data comes from it being available in sheer abundance. A single data point might not be telling, but string tens of thousands or even millions of those, and it paints a vivid story. We can look at this in the context of describing the pandemic. When data is taken straight from a source, such as the increase in the number of cases each day, it is deemed as raw data. Raw data is unprocessed and can be overwhelming at large volumes for people to make sense of just by looking at these numbers. This is where we turn to derived data to get a general sense of what all those figures are telling us. Derived data, unlike its raw counterpart, is processed and transformed. The aim is to make the data more readable by giving an overall metric that represents the set of data as a whole. Statistical measures such as the arithmetic mean is one of the many examples of derived data, a tool used to summarize a set of raw data in a concise manner. We can organize such data in a relational database due to the fact that it is structured in nature. This can be compared to what we typically see in Excel sheets, a table expressed in rows and columns, with each data point under a particular header. In the realm of structured data, we can capitalize on existing data to make rough predictions on what we might expect of future data entries. The most basic of predictive modeling techniques are based on mathematical regression models which attempt to find a relationship between variables. To illustrate this concept, let's use the data on the number of COVID-19 cases in Italy for the most simplistic and stripped analysis. I've put in place some Python code that will perform an exponential regression using the data.csv file I've available as input. In this function, I first defined the exponential equation in the generic form of a times e to the power of bx, where a and b are constants to be determined. After which, I load my data and plot the x and y values on the graph, which represents the independent and dependent variable respectively. In this case, the number of days since February 15, 2020 is the independent variable. These are the control inputs whose variation does not depend on another variable. On the other hand, the dependent variable represents the total number of COVID-19 cases in Italy x days since February 15. A dependent variable is one that varies depending on other variables. Since we are interested in predicting the number of cases, the regression will be set up in a way that estimates the value of variable y with respect to the variation of x. This is done by calling the curve-fit function. It takes in a series of arguments to plot the Bestfit curve for our dataset. The first is the predefined exponential function that we are modeling, followed by the x and y values we have, then p0 to initialize a guess on the values of a and b so that the function can eventually reach its desired local minimum. We can see from the list p of the values of a and b that gives the exponential curve the best fit amongst the data points. This is achieved through the Levenberg-Marquardt algorithm that performs least squares curve fitting, giving an optimized equation of our regression curve as shown. The idea behind least squares curve fitting is to minimize the sum of squared residuals, S. Mathematically, it is represented as such, but there is actually a much more intuitive way of understanding this optimization problem. To do so, we first need to know what it means to draw a Bestfit curve. A Bestfit curve is one that is closest to modeling the actual relationship between the independent and dependent variables, x and y. To achieve this, we want the collective distance between the y values from our data and the y values formed by the curve to be as little as possible. What we can do is to calculate this distance for every value of x that is in our dataset, given a set of parameters for the function of our curve, beta, which in this case is a equals to 80 and b equals to 0.195. This distance is called the residual. The square of this distance, known as the squared residual, is then computed for each value of x and added together to form the sum of squared residuals, s. The goal is to minimize this value by changing the values of the parameters to get the best results. Through the Bestfit Curve, we can visualize the relationship between x and y. It is good to note that this is an extremely simplified model that involves finding the correlation between two variables to estimate the growth of the total number of cases in Italy. Like all models, strong correlations are not proofs of causation. They are not gospel truths, as it only demonstrates that certain variables are associated with each other, which may or may not be purely coincidental. In this context, it is true that the number of cases does generally increase exponentially in the early stages as the days pass, but this is far from the complete picture. In reality, there are many other conditions that may affect the rate the virus spreads. For example, the efforts of healthcare workers and the effects of quarantine policies, which are not factored in our basic model, do significantly affect the trajectory in which the number of cases grows. As the virus gets contained, the curve flattens out, easing itself into a plateau as fewer people get infected each day. This phenomenon can be modeled by the SIR model, which is a step above our exponential regression. More realistic models will take into account numerous other factors as well in order to generate better simulations. However, this does not mean our model is completely useless. Our regression still provides value to us as it warns us of what will happen initially if we allow the virus to spread uncontained. It gives us an intuition of the scale of the problem and serves as a wake-up call for all of us to take action immediately in order to not let the situation spiral out of control. Structured data is cool and all, but most of the data in our world are unstructured, manifesting itself as text articles, images, videos, and other forms of media we consume. Wouldn't it be great if we could make sense of them as well? This is where artificial intelligence comes into play. In March, a Canadian AI firm, BlueDot, was in the news for predicting the outbreak way before anyone else did. The unique thing is that they are able to do so by using unconventional data types, such as news articles written in various languages and airline data. It can see through all the noise from the vast amount of information in the internet and pay attention to elements which are important using its neural network. While we can comprehend and appreciate the conclusions AI provides, and sometimes they really do produce valid interpretations, the process is generally a black box to people. AI is wonderful and should be developed further, but we should always remember to use it as a tool to complement our critical thinking ability instead of replacing it completely. Today, as we continue to fight against the pandemic, let us be reminded of what the data around the world has been telling us. Do take action today for the benefit of yourself and for others. Stay alert, not anxious.